surface area is intermolecular forces just holding all of them into a very low potential energy system. So we all know that if my hands are out here, what kind of potential energy do I have? High potential energy, and then I go to... So nature favors low energy systems in all ways. Even when we look at electron configuration, we know that electrons enter orbitals of lowest energy first. You guys are all confused. You're on the wrong slides. We're still back in intermolecular forces too. Remember, we have to finish that? So go back to those slides, and you'll find surface tension. All right, so back here with surface tension. So for high potential energy and low potential energy, things that are closer together, molecules that are closer together, that have strong intermolecular forces, are going to create the lowest potential energy system. So think about how molecules bead, water beading on a freshly waxed car. Wax is nonpolar, right? Water is polar. So the beading effect is even more enhanced because like dissolves like, we know that. So if it's nonpolar and polar, then they're going to do essentially this on the car. They're going to stay apart from one another. So if you can envision if I kind of just spill water all over my bench, it's just kind of going to go everywhere. But you may see some of the molecules find each other and create a bead. And so that's because this sort of system, all flat and high surface area, is a higher energy system because you have a lot of potential energy in that, right? The molecules are spread far apart, but what they really want to do is create that bead so that they can reduce their potential energy and all of those intermolecular forces kind of get tucked in neatly. So what you're looking at here is that this is the bead that's formed, and the intermolecular forces on the center end up canceling each other out. Like the net pull or push in any direction cancels itself out because they're in a bead. They're surrounded by all of the same molecules. But on the surface, we have nothing pushing or pulling on the surface of the bead, right? The only intermolecular forces that the bead is experiencing are inward, net force driving down in towards the center of the bead, which is why on the surface it all starts going in towards that bead. So you create intermolecular forces all towards the center there. That's what this slide is saying. The next one is talking about how the force vectors cancel each other. So there's no net attraction. The net force is going down. And then this reduces the potential energy of the system. So by decreasing the intermolecular forces, not decreasing them, decreasing the length between the molecules' intermolecular forces then decreases the potential energy. So again, net force of attraction is down, which give molecules on the surface more potential energy than the ones in the interior. The interior are pulling very tight together. The system becomes more stable when its potential energy is reduced, and the way to reduce potential energy is to create the sphere. So you reduce surface area, you increase surface tension, and then you therefore reduce potential energy. Does that make sense? Surface tension is essentially how, and you know this, that insects can walk on water, right? It creates almost like, with water, almost like a net. So you can envision like a really small, like a butterfly net, where all of those little molecules kind of are just holding on to one another. So besides insects walking on water, you can also probably think about experiments that maybe you did in middle school or something, where you take a penny and you add droplets of water to the penny and you try to see how many drops of water you can put on the penny. You're basically testing surface tension. And you create, the more water you add, the stronger that surface tension becomes. You have to increase the surface tension in order to have it sort of sit neatly as that bead on top. But then at some point, you're going to break the surface tension, meaning you've added too many molecules of water and it can't hold itself into that sort of spherical, ballish shape, right? Even when you add water to the top, like the very top of a pail, maybe a pail's too big, but my teacup, you can see actually like a little bubble that goes on top as you begin to add more and more water. And that is the surface tension. If you increase surface tension, you can actually get on the top of, say, a beaker here. If we fill this up, which we will try next week, as we do we're going to do a bunch of intermolecular force tricks in our lab, so you can test all this stuff. But you can fill this up so that it creates that sort of bead on top of the surface. And if you add more and more water, you actually increase the surface tension, and you can take a paper clip and just rest it on the top of the water rather than it sinking to the bottom, because the surface tension holds the paper clip in place. But you have to actually build surface tension. Without surface tension, it won't hold the paper clip. So you have to keep adding water so that more of that tension builds and creates that bead effect. So go ahead and read this about surface tension. It's essentially what I just said, except adding intermolecular forces. So stronger intermolecular attractions have greater differences in potential energy between the interior of the surface. Energy must be added to a liquid in order to decrease its surface tension and increase its surface area. Surface tension decreases as temperature increases. And that should make sense also to you. I mean, we're going to talk about viscosity in a moment, about temperature. But if you're increasing temperature, what are you doing to the particles, the molecules? If you increase temperature, what else then has to happen? How do they do that? It's on the board. No, it's not on the board anymore. It was on the board right here yesterday. If I increase kinetic energy, I gave it to you. If I increase temperature, I increase kinetic energy. So as soon as I say temperature, you have to think kinetic energy. That's what happens now. From now on in chemistry, if I say temperature, you think kinetic energy. So if you increase the temperature, then the kinetic energy is increasing. Your surface tension that was like this nice little net almost, this web, now you've increased kinetic energy and it starts to move around, and that nice tight surface tension starts to decrease because the molecules are held loosely. All right, capillary action. You guys have done this with a straw when you were little. You would suck up the chocolate milk or water or whatever you're doing. You hold it in the straw. This is sort of indicating a little bit of pressure is shown here. They're not indicating that clearly. If you just stuck a capillary or a straw in a liquid, it's not going to rise all the way up unless some sort of pressure is applied. But what we notice, probably didn't notice this ever because you're using a plastic straw, but in class you may have noticed with glass graduated cylinders. I'm not sure that you guys have used glass capillaries before. That would be like a glass pipette. You'll actually see that meniscus forming, and that's due to adhesion and cohesion. So you all know the meniscus is when you have your graduated cylinder, and I always tell you, right, to read the line right here. You don't read the line up here, you read the line down here. This part up here is due to adhesion to the walls of the glass. Glass has intermolecular forces with the water, so the water adheres to it. Like dissolves like. So if the glass is like the liquid, then you're going to see adhesion. Cohesion is when the water molecules, or whatever the liquid is, are sticking to each other. So they're pulling inward to create that surface tension or that bead, but the adhesive forces are pulling them up and out. So think of, you have to memorize these words if you're not familiar with the prefixes, but think of adhesion like an adhesive, Band-Aid. You put the Band-Aid on your skin, it has adhesion because the glue is sticking to your skin. So it's two different substances sticking to each other. Adhesion is the liquid to the glass wall. Cohesion is with itself. So this is an exaggerated effect of the meniscus here. So the liquid is traveling up the glass walls. It creates adhesive forces, and you see a meniscus. In this next slide, this is not such a severe meniscus. So which one has stronger intermolecular forces with itself? The deep meniscus or the shallow one? Yeah. You have a very small meniscus when the cohesive forces are strong, right? You have that really deep meniscus when the adhesive forces are stronger in a sense. Well, they are stronger in the second slide, but the cohesion forces are weaker in this, so more of it can adhere to the wall. And then the liquid here has it does have stronger cohesive forces than that last slide, but the adhesive forces are overcoming the cohesive forces. If the adhesive forces did not overcome the cohesive forces, then what would it look like? So you don't have adhesion anymore because cohesion is overcoming it. It would be the other way. So this is an example of mercury, which has stronger cohesive forces than adhesive forces, and you actually see the opposite here. So you see sort of like a bubble up. All right, viscosity is another vocab word that you should just memorize. And this seems so common to me because we even use the word viscous in our house, but maybe because Mom is a chemist. But how many of you understand the word viscous besides this lecture? 1, 2. Maybe. You don't go home, say to your mom, can I have some viscous maple syrup? Viscous molasses, those are viscous substances, right? So maple syrup, you can envision that's thick, right? Molasses are really thick. There's other thick substances, right? You can make like, if you put sugar or confectionery sugar in water, you can make icing. So you can make it thick and liquidy, so it's very viscous. So viscosity is a measure of the substance's ability to flow. So if it flows easily, it's not viscous. If it's not flowing, it's very viscous. You can decrease the viscosity by increasing temperature. So if you put your maple syrup in the microwave to pour over your pancakes, your syrup now becomes much more runny, liquidy. How many of you do that? You guys just put like room temperature cold syrup right on your pancakes and waffles? I'm going to introduce you to a new world. It's called hot syrup on hot pancakes, and it's amazing. Your food doesn't get cold. It all stays very hot while you're eating it. Try it one day. Pour a little bit in a cup and microwave it, and then pour it over it. It's like pancake luxury. You'll enjoy it. All right, the next few slides are biochem related, but you would not have to be able to draw any of this or even answer questions about proteins or nothing. All it's ever going to ask you to do is look at a structure, identify where maybe hydrogen bonding takes place, identify where a structure is kinked because of intermolecular forces. They might show you a structure where the inside is a certain intermolecular force and the outside something different. So in this case, what we're looking at is the dehydration process where you remove water from a reaction. So these are two different molecules. You can see where the H2O bonds are going to form here. The water gets removed, and then the nitrogen attaches to that carbon there, and you create a bond. So you can create a new molecule. That's organic chemistry, like 101. You're going to start learning how to make reactions. This is showing you another example. Here's your protein structure. At the end there, you have where the water could actually be dehydrated again, and you could actually create a chain structure that kind of links over and makes a circle on itself. You can do all sorts of reactions with them. This is showing you a DNA strand. So your R groups, by the way, are your functional groups, right? It just R means something else. So you certainly have seen DNA in cartoons and magazines where they show you the helix structure, right? You probably haven't seen the beta pleated, but you've taken bio, you know at least something about that. So how does it create an alpha helix on itself? So what it does is it has hydrogen bonds here. Hydrogen is attached to nitrogen, oxygen, or fluorine. Lone pair oxygen, it finds itself and it kinks. So now your chain wraps around itself in order to create a helix structure. So all of these little red dashes are your hydrogen bonds in here. But you could also create the beta sheet because if it ends up finding the hydrogen bonds where the chain just keeps wrapping on itself, then they kind of stack on top of each other neatly like that versus creating the helix structure. Same thing with this. So envision you have a long chain here, a protein. It finds hydrogen bond spots. It also finds London dispersion spots. So as they create hydrogen bonds, it draws the molecule in towards itself. Here's another example of that active site. This is sort of like that lock and key system that I was talking to you about, how molecules end up creating that active site so that way it could inhibit or enhance a function. So they create shape to their long chains. This one is creating a nonpolar center by putting all London dispersion forces on the inside. So very nonpolar on the center, but very polar on the outside so that hydrogen bonds can form. This is again just showing you how two different long chains can come together through hydrogen bonding or London dispersion. All right, polymers are something that you should be familiar with. Polymers are plastics. So polymers are basically a long chain of carbons. Sometimes they have other pieces on them, but very, very, very long chains. And so you're basically only creating London dispersion forces here, but the longer the chain, the more electrons, the more polarizable it is, so you have strong London dispersion forces between all of your chains. Polymers are flexible because they're just held together with London dispersion forces. That means that you can mold them and shape them easily. It says that, that's it, they can be molded or shaped. So what I was going to just mention to you, some of you have seen them before. I can't believe I didn't have one today, but those little baby test tubes, oh, maybe it's in this drawer. I looked all over for them. Still can't find it. But the little baby test tubes, you guys remember me having these around? They're like soda bottles, essentially like this, but they're miniature. They're like this big. So think about Coca-Cola getting all of their millions of bottles of soda shipped to their factory, or having to, they don't make their plastic containers, I'm sure, but they get them all shipped to them. And then they have to fill them all with soda and then ship them out. Well, if they had to ship all the empty bottles to their factory, that would be a whole lot of empty space, right? Just used up, it's just air in here. So what they do is they ship little mini soda bottles, and because they're plastics, they can put them into their heating system, into a mold, and they actually can blow them, kind of like how you would blow glass, into the mold of whatever shape bottle that they want to make, which is why we have different shapes. Like this mold must have ridges in it, right? So you're not just sending empty bottles everywhere, you're sending little miniature ones, and then in their factory they blow them up, right? It would take up a lot of space if they had to store millions of empty bottles everywhere. So they store little ones, they blow them up, they fill them with the liquid that they need to be in there, and then they ship them out. All right, so we're going to pause